How's it going? Alright, so we've already talked about statistics being a goal, having a goal of collecting data, and we've already discussed a little bit about how to organize that data. It's now time to start actually doing some real calculations. And so we want to talk about the first of our calculations to organize and maybe even begin to analyze data just a little bit with discussions of what we call central tendency. Central tendency has this word central, which means the middle, and tendency, which is this idea of here's what you tend to do. So if you watch waves, they tend to go up and down, so that's very interesting. If you talk to professors, they tend to say it's in the syllabus. And so we want to talk about what's in our numbers. We've got some specific ideas of central tendency, and what we're going to find is that those ideas behave just a little bit differently depending on what exactly we're doing. So first of all, let's talk about median. Median, just like that thing in the middle of the street that's cement and you can't cross it, it's right in the middle. Median is all about finding the number in the middle. Medians, if you have an odd number of numbers in your list, pause that and let me say that carefully. If you have an odd number, an odd count of numbers in your list of variables, then you just take those all in a row. Let's say we've got 5. You can say there's 2 on this side, 2 on this side, and the one in the middle is your middle value. That's the median. I think I just gave you guys the finger, and I apologize for that. If you've got an even number of numbers, however, you're going to have 2 things in the middle once you take the 2 on each side there. And so you're going to have to take these 2 in the middle, add them together, and divide by 2, and we have our first new symbol. This. It's a capital sigma, and it means sum. Add them up. Add up the middle 2 numbers to find a median if you've got an even number of things in your list. We're going to use a lot of Greek characters in stats, and it's going to be very important that we can tell the difference between them. So I'm going to always, at the beginning, write out to you what the symbol is and what it means. And of course there's reasons why we do this. But think of this as one extra area where you can sort of stretch your mind and get used to some new ideas. There's a reason behind it. So let's take a look at this list of numbers. I've just randomly generated them, but I've taken the efforts to organize them in order. There are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Looks like there's 25, my favorite counting number there for random numbers that we've got. And to find the median, I need to find the one in the middle. It's going to be the total middle value. We've got him right here. There's 2 rows above him and 2 rows behind him. There's 2 on the left and 2 on the right. This number right here, 34, is my median value because I had an odd number. It's a very nice value. Notice these numbers are as small as 2 or as big as 80. 34 is the one in the middle. Advantages of median to describe central tendency. There's 25 numbers in that list. I don't want to list all of them off to you every time I want to talk about the idea of that. Let's say these are salaries. Again, salaries in thousands. If I say that the median salary is $34K, you say to yourself, yeah, half of everyone makes less than $34K, half of everyone makes above $34K. $34K seems a pretty good number to describe the salaries. Possibly. But that's only one perspective. Let's take a look at this smaller list. We'll call this other example. This is a more extreme list. Let me try to write the number 34 here. What if we only had 3 salaries? Some super miniature company or some micro country. 34 would be your median salary. Half of everyone makes less than that. The other half makes above that. But obviously 34 is a pretty small number. Doesn't really compare all that well to the person pulling 100K. And it doesn't compare all that great either. It's way bigger than that 0K. So median isn't always a really good fit, but still it's the one in the middle, no matter what. Let's make this more extreme. Let's say we've got a Bill Gates there or something. I don't know what Bill Gates makes in a year. Let's say he makes 500K. Again, 34 is the number in the middle, but he's a lot closer to this 0 than he is to this dude making 500K. Mode is another way we can talk about usual. Another way we can talk about central tendency. Mode is the number that shows up the most. In this small example, I don't have a mode. Each number only shows up once. However, here I do have a mode. If I look through these numbers, I see that the number 45 is shown up 3 times. "34 may be the number in the middle. That's what the average person, if I wanted to use that dodgy word, average, makes. But a lot of folks make 45K. 45 is giving us another idea of central tendency, because you can't say that 45 isn't a common number. It's the most common. A lot of people make 45K. 3 of them, in fact. Each of these, median, mode, could be what we mean when we say the word average. The word average is very ambiguous in statistics, and so we do our best to ignore it. Incidentally, I talk about Excel a lot, and now's the time to tell you, if you type in equals median into Excel, you will get yourself something that will allow you to highlight a list of numbers, and it will give you the median number. It'll do this middle value, or if it's even, it'll take the average in the middle too. You can also do mode, and Excel equals mode. And then type in a list of numbers, and Excel will give you that as well. But I would have to say, in general, the most common thing that we mean by average is this, which we call, oddly enough, mean. M-E-A-N. Mean regression. This idea of some sort of central number that we can get. And once again, you see that I've used some very complicated symbols to describe something that probably before you already knew what to do. If I asked you, what's the average of 0, 34, and 500, you would know precisely what to do. You'd pull out your calculator, and you do what? You do 0 plus 34 plus 500K, and you get yourself 534K, and you would divide by 3. And you get 178. You would call this average, and in fact, if you wanted to do this in Excel, you would even type in equals average. But in statistics, because we need to be precise, we're trying to explore relationships of data deeply, we use the word mean, and what we did is we added up each of the values, and we divided by the head count. That's what this symbol here represents. Remember, this symbol right here is a Greek character that means sum. So I say sum up all the x values, these are the x's, divide them by the head count. How many of them are there? These are the n's. In this case, n equals 3. If we do it for a small group, if we do it for a sample, you will find that when we talk about samples, remember samples versus population, statistics versus parameters from the first video we had. If we talk about sample data, you will find that we use Latin alphabet characters that are lowercase. So lowercase Latin alphabet for samples. Sometimes, though, we talk about populations. And when we discuss populations and statistics, you can know right away from the formula if we're dealing samples or populations, because populations will use lowercase Greek letters, not lowercase Latin. And if they do use Latin letters, they'll use uppercase. Side note, not too much of a side note, but a little bit of a side note. Sometimes I notice students who write things like this. If you were doing algebra, you'd write lowercase, and that would be lovely. But sometimes I've seen students do this. This is a terribly bad habit that you must instantly and forever, right now, break yourself of. In statistics, we talk about samples versus populations. And the way we distinguish between those is with lowercase and uppercase. So you must be terribly careful that you're not one of those people who seems to automatically convert everything to uppercase or everything to lowercase. You must use the letters that we use because we're going to use other letters later on for other stuff. I once complained bitterly when I was studying for my math exams that what we should do is we should use Chinese characters because they have a different character for every word, and then we'd never run out. 26 times 2 doesn't seem enough, and it's not. We have to add in the Greek ones. In fact, we're already using a Greek character. This is a Greek character for sigma. Mathematicians tend not to be very inventive, and our statistician brothers don't change that much. Capital S in Greek is this character right here, capital S for sum. Sum them up. So sum up all the x's, divide by n. This is what we call x bar, x with a little bar over it, and x bar means mean, which is the traditional average. Technically, if you want to get precise about it, the word that most people use for average, add them all up and divide by the number, is called the arithmetic mean. Arithmetic for adding them, mean for, well, mean. Written out, long form, it's 0 plus 34 plus 500 divided by 3. N is 3, summation x is 0 plus 34 plus 500. And that's what we talk about when we think of the word average. If we want to do population, that just means we're going to have more. We're not looking at just a few people in our country. We would look at absolutely everyone's salary in the whole country and divide by, what, 300 million for the United States, 302 million maybe now. Sample mean, population mean. These are the differences. Let's go ahead and stop looking at this teeny example for a second. And let's look at this bigger example. Same idea. We want to calculate x bar. We're going to add up all the x's and divide by the number of things here. There's 25 of these, so I'm going to divide by 25, and I start going. 2 plus 8 plus 11 plus 14 plus 17 plus 18 plus... This gets rather tiresome to write, so let me introduce you to another math symbol. Plus dot 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 plus 80. It gets boring to write all of these things out with pluses. So we write dot dot dot. This is called ellipse. And the triple dot means continue doing the obvious thing. I'm adding up all these numbers. Continue doing that all the way up to the end. And when you get to the end, stop. It gets boring, though, to write a whole bunch of pluses and an ellipse. So we came up with the Greek symbol, capital S for sum, because we're summing all of these up. This is terribly important notation to get burned into your head right now. So be careful with capital and lowercase letters. Be careful with what we mean by sum. And we would like to find the sum of all of these numbers, and when we've done that, we're going to divide by 25. But now it's time to show you something rather cool. It would be rather boring to type all these numbers in and keep on writing plus, 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 and then divide by 25. I would personally rather not do that. Certainly for 25 numbers, absolutely for sure if I have 5,000 numbers. So let me show you something on your calculator, if I can hold it here. Notice on your calculator there's this little piece right here that says data, and right above it it says statistics, regression, distribution. Our calculator is capable of performing some statistics for us. So what I want you to do is pull out your calculator, go ahead and make sure it's on, and anytime you're doing your calculator, let me recommend doing this every time you're doing a new one. Go ahead and hit second, go ahead and hit 0 for reset, and go ahead and scroll down and tell it yes and hit enter. This will clear out your calculator, and then once you're ready to be done with that, then you can hit the clear screen. And this way you know you're not accidentally recording old numbers with some of your new numbers. It guarantees that you do your statistics cleanly. So review that, refresh that, get comfortable with that. Fair warning, if you bring your calculator to an exam, that's great. I strongly encourage it. In fact, I don't think you can do it without this. I have been known to walk around at the beginning of exams and hit clearing these things just to make sure you're not hiding anything strange in here. But I want to type in these 25 numbers, and I would rather not calculate the average by myself. So instead, I'm going to make the calculator do it. You could use equal average on Excel, and it would give you the same answer. No problems there, but let's talk about the calculator. Go ahead and click Data. And when you click Data, notice on the screen that it gives you this list of numbers that you can put stuff in. We tend to use the first list only, so I'm going to go ahead and do that, and I'm going to start typing my number data values in there. I've got the number 2, 8, and 11, and 14 on my screen up there, so I'm going to type in 2 and hit Enter, and then I'm going to type in 8 and hit Enter, and then I'm going to type in 11 and hit Enter. And you see how I'm doing this? And so I'm going to go ahead and type this in large form. All right, I've got 14, 17, 18, 21, 25, 26, 27, 31, 33, 34, 39, 40. Oh my goodness, we're almost done. 45, 45 again, 45 another time. Incidentally, your calculator's clever with lists. You could do something in the second list. I'm not doing it right now. I'm just typing these all in raw. But you could have typed in 45 in list 1 once, and then over in list 2 in that spot, you could have typed in 3. If you have a lot of repeats, that could be a time saver. But I prefer Excel for that sort of thing. 52, another 52, 55, 56, 57, and finally 80. We are done. I have entered in 26 things into my list. Look at the bottom here. Excuse me, 25. Notice it says list 1, position 25 when I highlight the 80. If I scroll down, it would be in position 26, but you can see what position each of these numbers are in. You do not have to enter the list in an organized fashion. If you had raw data values that were all chaotic, calculator could still cope with that. That's fine. Once you've got your numbers in the list, you're going to hit second, and then you're going to hit data again, and this time it will do statistics. You're going to scroll down to one variable, statistics. You're going to go ahead and hit enter. And you're going to tell it that the data is stored in list 1 and the frequency is 1. Frequency of 1 means that I entered each of these guys in as many times as they showed up. So the 45s, I entered 45 in 3 different times. Again, like I said, if you use list 2 to tell frequency, then you could select list 2 as your frequency. But we're going to select frequency of 1. It's our most common thing to do. I'm going to scroll down then to calculate. I'll go ahead and hit enter. Now my calculator is giving me quite a lot of data values, but the one I care most about is the top one. Notice that it says n equals 25. I knew that already, but it's nice to confer. Notice the one right below it, x bar. It's got a number for x bar for me. It's done this calculation of adding all of these up together and dividing by 25, and it tells me that x bar is equal to 35.28. But if you continue scrolling down, you'll find some other things that it gives you. And we'll talk about all of these eventually, but I like number 5. Notice it's the sum of all the x's. X bar equals the sum of all these numbers divided by n, which we said was 25. And if I added all these numbers up together, in position 5 on your screen, it says 882. If you added all these pieces up together, you would get 882. Remember what I said about rolling up your sleeves and getting your hands dirty with the calculation. It's lovely that the calculator does that, and it's great. But you still have to understand why it's doing and giving you the answers you're giving, because that's going to make a big difference later on. So we've gone ahead and gotten ourselves 882 divided by 25. If I go ahead and take 882 divided by 25, let me tell you what it's going to give me. It's going to give me 35.28. Because that is this number. So you can definitely use your calculator to power through some of these problems. And the more you scroll down on your calculator, the more it will give you some interesting pieces. Here's some other things it gives. If you scroll down far enough to position 7, you're going to get the min. It tells you the smallest number. Now we can see that right away. If you scroll down to position 9, it tells you the median. The calculator calculates this for you. It says 34. Which is good because it was 34 and we'd already decided that. It'll also tell you the max. The max is 80. So this calculator can be a very powerful tool. And I want to take a second, just a second maybe, well actually more like a minute, to tell you something. I only allow the TI-36X Pro and Excel on tests. I could write a test that allowed you to use just a basic 4-function calculator. I could write a test that allowed you to use a TI-9000 that would be able to do whatever you wanted to for you. And it would be able to test your skill, not the calculator's skill. What I can't do is I can't write a test that does this for any calculator. So instead, I've chosen the sort of dodgy process of saying, this is the only calculator I allow, and Excel. You don't have to use one or the other. Either one can work. But those are the only 2 things I allow. And when I build the tests and I decide what time I should allow, I am assuming that you are very skilled at using either this calculator or Excel. That's why I strongly suggested in the last lesson that you use this calculator and practice through the in-text examples. As you're solving the homework, I suggest you use this. Get comfortable with it. Know what its foibles are. I think I mentioned earlier, if you add some numbers together and don't sum them before you divide, you can get something weird happening with the order of operations. So be very, very careful that you are proficient with some technology, because I've decided that this is the level of technology that should be accessible and fair to everyone. Enough of my philosophical rant. We have found the average, the mean, for our sample. We've talked about capital sigma for summation. We've got x bar as a sample mean because these are sample data. There's not very much of them. And I've even mentioned it's the same formula, notice. You add them all together and divide by the total number. But for population, we use capital N, and we use another Greek symbol, mu. Be very careful when you write it. It's not u, it's mu. And you can tell that because it's got this little tail here. Mu, mu is how it's pronounced. And we will talk about population means on occasion. Your calculator, because it's the same formula, is not very clever. It never tells you this number because you calculate the same way as this. So in your calculator you will only see x bar if you type in a whole bunch of numbers into a list. That's fine. You're clever enough to interpret between the two. Become familiar with the different symbols. If you've taken a look at your formula sheet, which remember you're allowed to use all the time, you will see that about half the formulas involve lowercase Latin characters, and the other half involve uppercase Latin characters and lowercase Greek letters. That means that if you can read a problem and decide whether it's sample or population data, you can usually cut that list of formulas that are possible to use in half. And that means you're a lot closer to knowing which is the correct formula to use. In this case, it doesn't seem to matter much because it's the same formula. But later on, we're going to have different formulas for different things. So let's take a look at what we've got. I've said that we're trying to understand a whole group of numbers with some central tendency. And so far, we've said, well, maybe that central tendency is 34K. Does that make sense? Well, kind of. We said maybe that central tendency is 45K. That also makes sense, but I am noticing there's a difference there, 34 versus 45. And then I said, well, maybe we could talk about this idea of average, the idea of adding everyone up together and dividing by the number of people. In which case, for our list of salaries over here, the average is 35.28. Rounding convention time, remember last time we discussed how you were going to round for class frequency, and we said always round up to the next highest integer. Here we're going to use our normal rounding techniques, and however accurate your data is, we will round to one more decimal place in general, unless asked to do otherwise. So I would actually round this to 35.3. I'll put a little wiggly equals here to show that that's an approximation. My raw data is no decimal places, so I go 1 decimal place over. That lets you know that I'm doing a calculation as opposed to having actual raw data. It's part of that idea of data validation that we talked about at the very beginning, having good data and making sure you don't miscode happy or sad. So let's look at the numbers that describe this list of salaries. We said that 34 might be a good number, and we could call that the median. If I wanted to collapse all these numbers to a single number, a single data point, and say the usual person in this group makes 34K, would that be fair to say? Well, maybe. Maybe. But this dude making 2K a year isn't going to feel pretty happy. Dude making 80K a year will feel cheated if you suddenly try to write him a check for only 34K. So maybe that's not the best central tendency number to look at. Maybe the mode is. These 3 people will feel spot on if you say 45K is what the usual person makes in that list of numbers. However, lots of people are going to feel unhappy if they're told 45K is what folks make. And again, you'll still have some people up here at the top that say, I'm not feeling it. So maybe mode also isn't so great. Well, what about average? This idea of mean. X bar is 35.3. It lives maybe right here. Good things? This 35.3 seems to tell me that, look, there's some pretty high salaries up here. Bad things? Over half the people make less than 35.3. Even worse things? No one actually makes 35.3. There's no dude here who actually makes the average salary, this X bar. All the numbers together are the correct answer to try to understand central tendency. And that's what we're looking for. We don't necessarily need a single point number. Instead, we would like to talk about all of them. However, it comes with a risk. And here's why I think getting your hands dirty in the calculation is beneficial. In this group of numbers, 34, 35.3, and 45K all seem to be kind of close together. They're very close to matching. That makes sense. Overall, I would say those numbers describe this group pretty well. Not perfectly. There's a big difference between 34 and 45K. However, in this smaller example, which I've made to be looking a little more extreme, you see the difference. The mean is 34, the median is 34, the mean is 178K. If I said the usual salary in this list of numbers was 178K, was a decent solid 6 figures, you'd say you're crazy, and you'd be right. Here's the thing you have to watch out for. When you have extreme values, those outliers that we talked about last time with the CEO salary, when you have outliers in your data set, it can skew your mean calculation. And if you have very few numbers, they can even skew your median. Mode's always pretty solid because lots of real honest-to-goodness people actually make that. But still, you have to be careful. So what should we do? Well, sometimes it's convenient to calculate what we call a 5% trimmed mean. You cut off 5% at the top and bottom of your data values. So let's take a look at what that would do here with these numbers. If you're inside your calculator and you're inside your statistics place, that's okay. You can go ahead and hit second and quit, and you'll get back to a screen. What I'm going to do is I'm going to take 25, that's how many numbers I've got here as a head count, and I'm going to multiply that by 5% times 0.05. Here's my calculation. Go ahead and hit enter, and I get 1.25. My rule for calculating a 5% trimmed mean says that we're going to round to the nearest integer. And we're going to just use our normal rounding process. So here I've got 1.25, and I'm going to round myself to 1. So for a trim mean, what I'm going to do is I round myself to an integer of 1. And that means, anyone? Yeah, okay. I'm going to cut off the bottom 5% and the top 5%. Here I'm only counting 1 off from each side because we rounded to 1 when we took 25 and multiplied it by 5%. And this means I can go back into my data column by hitting Data button, and I can go ahead and delete that 2, and then I can scroll down all the way to the 80, and I'm going to delete that as well. Now I only have 23 numbers on my list. I will go ahead and hit Second and Data again. Maybe I should show that again. Hit Second and Data again. Go back to one variable statistics and have all of this recalculated. And if I look, I now only have 23 people on my list. And if I look at my X bar, I have a new X bar. It's 34.78. Trimmed, I think, has another M in it. Yeah, I'm feeling 2 M's for trimmed. Trimmed X bar equals 34.78. So if I round 34.8. Is it a big difference? No. But it does code in a little bit better since I've gotten a little closer to this median, this idea that we have quite a few people here who don't earn as much as some of these folks at the top. 5% trimming, as long as you've got, let's say, more than 20 variables, can get rid of some of the outliers and give you a better sense of what's happening in the middle. If we'd gone back to that earlier example I did where we had everyone was kind of together and we had that positively skewed histogram and we just trimmed 5%, we would have cut off the CEO's salary definitely in that list of numbers, and that would have given us a much more clear picture. It would almost look normal if we trimmed off the CEO. It would have done a lot more of that build up and build down business. So, median, middle value if it's an odd number of counts, middle 2 divided by 2 if it's an even. Mode is the most frequent. Sometimes you don't have modes, that's okay. Sometimes you've got more than one mode. It's called bimode. We even saw a histogram for that bimodal stuff where you could have tri-mode or multi-mode. That's entirely possible. It's however many is the highest number, and if that highest number is repeated ever, then you've got that. Mean. We take the summation of all the x values and divide by the head count. We call that x bar for sample. We call that mu for population. And I also said samples have lowercase Latin characters, populations have uppercase Latin characters, and lowercase Greek characters. And I also said that sigma was a capital Greek letter, and we use capital Greek letters for operations. In this case, sigma s for sum. That pretty much wraps up my talk about central tendency, except for one last thing. Sometimes central tendency isn't just the raw numbers. And a perfect example of that is this class. If you take a look at your syllabus, you will find that we don't calculate things based on mean. Instead, we calculate a weighted mean. We call that a weighted average right here. And weighted means are very powerful. They allow you to say some things are worth more than some other things. So let's take a look. In this class, I think that we have some, and let's just grab, because I have it a little bit different for the online versus the face-to-face. You know what, let's not talk about stats at all. Let's talk about my finite class. I've got homework, I've got quizzes, and I also have midterm, and I have a final. What else do I have in that class? I guess that's about it. 30, 20% 20%. No, that's not how that one goes. It goes like this. This is a weighted average because homework is worth less than the quizzes. The midterm is worth less than the final. How do you calculate what your grade is? Well, you need two pieces of information, and that's what this says right here. You need to know your X values, and you also need to know the weights. So in the syllabus, I give you the weights, and then it's up to you to know your X% in each category. Now, inside any single category, all the weights are equal. So if you're doing your homework calculation, and this is true in stats or in finite math, you would go and you would take all your homework scores, add them all together, and divide by the total number of homework scores. And maybe that would give you some percent. With rounding, of course. Then you could do it with the quizzes. If you followed the hour outline steps that we talked about last time, I suspect your quizzes will be going quite well. There seems to be a magic number. If you have your homework above 90%, and you've done all the work required to make that happen so that you're practiced and skilled enough there, then the quizzes tend to be in the C or higher range. Anytime the homework drops below 90%, that's when I start seeing the quizzes start to drop very fast, because quizzes are timed and single try, and that makes it more challenging. You have to be practiced. Again, math is not weekend warrior gym business. It's everyday practice. Don't take the quizzes right after you've finished the homework. Let that percolate in your mind and rest up. But if an 83% here, I would probably expect the quizzes to be something like 68%. And that just goes to show that 92% for the homework is vital. And also, let's say that someone had managed to score themselves a 60% on the midterm. Incidentally, this list of numbers is pretty common for an 83% homework. You have to be skilled at the homework, which is multi-try. And if you're good at that, then you have an opportunity to be good at the quizzes. If you're good at the quizzes, then the closed book final exam and midterm won't be too bad. What is this person's current grade? Well, it's a weighted average. It's a weighted average because we have to take each of their scores times the weight and divide it by the weights. We tend to convert these to decimals. So for homework, I have an X of 0.83 times a weight of 0.2. An X times a weight, then a sum, so plus. Then I have a 0.68 for the quizzes times a 0.3 for the weight of the quizzes. An X and a weight, an X and a weight, and then a sum, plus an X and a weight. And you divide this by the total weight. We shouldn't divide by 100% because we haven't taken the final yet. So we only add by the weights. 0.2 plus 0.3 plus another 0.2. Weighted average. So again, I can do that calculation. I should watch out that I do that carefully. I don't know if I go into my calculator here. Possibly I hit the fraction bar to create some sort of grouping process. And then I'm going to do parentheses. 0.83 times 0.2. Close the parentheses, hit a plus. 0.68. Let me see if I can get all those things in the viewfinder there. 0.68 times, and I should probably put parentheses in front of that just to make sure it goes well. And you can experiment, times 0.3. Close those parentheses. One more plus, one more open parenthesis. 0.6 times 0.2. Close the parentheses. Go down. Let's divide by 3, 4, 5, 6, 7.7. I went ahead and added those up. Scroll to the right, hit my enter button, and I now have my weighted average 0.7. This looks pretty good for this person. They've left the midterm and they have 0.7, which we would probably call a 70%, which under my grading scheme would give this person a C. You would get your midterm letter grade and it would be a C. And yet, for all that, I would tell this student, be careful. Be terribly careful. You've got to get a better, more grittier work ethic, deliberate practice. Because if you've scored a 68% on the timed quizzes, where maybe you have some examples and books and stuff open, as well as the formula sheet, and you only have a 60 on the midterm, which only covers half the class, and 30% of the grades the final, which covers the rest, I would be very concerned that this final exam score would probably be closer to this than anything, and that, at 30% of the grade, would drag this down suddenly into D territory. So, weighted average, trimmed means, sample versus population means, mu versus x bar, mode, and median. All of these measure central tendency, giving us a couple numbers that let us take a large group of things and collapse it down to a single value, or a couple of single values that we can look at. It's the first step to understanding how data works, to taking a large complicated problem and collapsing it into something more straightforward. This section on central tendency is powerful. Let me give you just a bit of a hint as to where we're going next. Where we're going next is to go just a little bit further. Instead of talking about central tendency, I want to talk about turbulence in my data. What I call wiggle, what our book, and all scientists, call variance and deviation. Think back to my analogy of waves. If the waves are crashing on the shore, they wiggle up and down, and there's all sorts of random data stuff they could do. However, at any particular time, there's probably a line on the shoreline about where the water height is. That's central tendency. But the fact is, if you stand a little bit above that line, and a wave comes a little bit higher, it could still splash you. Or you might stand a little bit below that line, and if it's at the trough of the wave, it won't hit you. The wiggle of the waves is variance. It's change. It's turbulence. It's the difference between rafting down a nice, peaceful, placid river and going whitewater rafting. You might travel the same distance. You might have the same amount of water in the river in terms of depth, but the whitewater rivers will have a lot more variance in height versus the placid stream that has a very little variance in height. So as we're trying to analyze numbers, as we're trying to do our best to create a model for the real world, we care about central tendency. We care about these different types of it so we can get a sense and see, is there anything that's common, uniform? But we're also going to care about variance. So, practice this section, practice the recommended exercises, play around with your calculator to get comfortable with entering things into it real fast, and I will see you next time. But until then, be safe.